Exercise 7 next. Again, like before, here also we have to find the degree of the splitting field of this polynomial over f, which is the field of rational numbers, and p of course is any prime. So the solution starts off like this. Since f is the splitting field of the polynomial x square minus 1, we assume p to be odd. What does it mean? We are saying that f is the splitting field of the polynomial x square minus 1. So that is why we can assume, and we are assuming, that p is an odd prime. That means the case where p is the even prime, 2 is the only even prime and it's the smallest prime, that in that case already the result is true. Why? Because when p is 2, then your polynomial is x square minus 1, which of course is reducible, and it reduces over, or it splits completely as a product of linear factors over f itself, the field of rational numbers, and you already know how that happens. X square minus 1 is x plus 1 times x minus 1, where both the linear polynomials x plus 1 and x minus 1 are polynomials over the field of rational numbers. So that means over f itself the polynomial splits completely. So we need not even extend f to an extension which is different from f, and that is why clearly f is the smallest possible extension over which the polynomial splits completely as a product of linear factors, and that is why f itself is the splitting field of this polynomial. That's what we have written. Since f is the splitting field of the polynomial, so, and what is its degree over f? 1, which is 2 minus 1. So in this case 2 minus 1 is p minus 1. The result is already true. So that's why we assume now that p is odd. Okay. Now consider the complex number omega, which is this complex number e to the power 2 pi I divided by p. In other words, it's just this complex number with absolute value 1. This is just another way of writing this unimodulus complex number. We know from elementary properties of such numbers, or from elementary properties of complex numbers, that this thing is equal to 1. Why? Because the pth power of omega to the power j is also the jth power of omega to the power p, and omega to the power p you can clearly see. You can use de Moivre's theorem, or you can just use properties of this complex exponential to see that that value omega to the power p is 1. So this is 1. For all integers j satisfying these inequalities, right? Also, all these numbers omega to the power j are distinct. That also comes from the nature of such numbers. Also, these numbers are all distinct. So what does this tell us? It tells us that we have found p roots of our polynomial x to the power p minus 1, and those roots are omega to the power j. They are, after all, in general, they are complex numbers. That much we can say. So these are p roots of this in the field of complex numbers. In fact, all these roots actually belong to this extension of f. Keep in mind, f is the field of rational numbers for all such j. Why? Because by definition omega belongs to this extension of f, and these are just integral powers of omega, and because this is a field in itself, so all the powers belong to this. Note that any extension of f containing all the roots of x to the power p minus 1, that means all these omega to the power j's, must also naturally contain this extension f omega. All the roots of x to the power p minus 1 must contain f omega, because one of the roots is omega itself, and being an extension, being an extension of f, such an extension should contain f also. But this is the smallest subfield of the field of complex numbers containing both f and omega, so that extension also must contain this, and as such f omega now becomes the splitting field of x to the power p minus 1, because x to the power p minus 1 already splits over this field completely as a product of linear factors. Why? Due to the fact that this field contains all the roots of x to the power p minus 1. But now it also turns out that it is the smallest among all such extensions containing all the roots of x to the power p minus 1. So by definition it will have the smallest degree also, so it is the splitting field. Hence f omega is the splitting field of our polynomial over f, of course, that's understood. But now we need to show that the degree of this extension of f is in fact p minus 1. That's what now we have to show. And what will this degree actually be? Recall our theory. According to our theory, this degree will be the degree of omega itself as an algebraic number over f. That is over the field of rational numbers, which in turn is what? Which is the degree of the smallest non-zero polynomial that omega satisfies over f. So we now need to find, in other words, it is the degree of the minimal polynomial of omega over f. So we now need to find a non-trivial polynomial, of course non-trivial polynomial that omega satisfies and which is also irreducible. Irreducibility will imply that it is the minimal polynomial of omega. So that's what now we have to find. So we proceed like this. Since omega to the power p is equal to 1, this we have already seen before, and omega is not equal to 1, we have 1 plus omega square, etc. up to omega to the power p minus 1 is equal to 0. Okay, we understand this equation, but what about this? Why is omega not 1? You see, omega is not 1 because p is an odd prime. If p, in the case where p is even, our omega would look like this. I sin 2 pi divided by 2. Well, in that case also, it will not be equal to 1, it will be minus. This part is 0, this part is minus 1. But the fact is that since p is odd now, p is an odd prime, so this cannot possibly be equal to 1. It's just a simple thing to see why this is not 1 when p is odd. I leave that to you. Okay, for this to be equal to 1, of course this should be 1 and this should be 0. Then the properties of cosine and sine functions, you will see that something will be contradicted if you forcefully suppose that. That is why omega is not equal to 1. But where are we getting this from? We are getting this from the factorization of this, which you know from elementary algebra, it can be factorized like this. This is 0, this is non-zero, so this should be equal to 0. So that's how we are getting this. Okay, so that means what we have found is that omega satisfies a polynomial of degree p minus 1, and this polynomial is of course a polynomial over the field of rational numbers f. So let's see, and this polynomial, it turns out, is irreducible over. So omega satisfies the polynomial 1 plus x over f. That means it's coming from the polynomial ring fx. And we already know that this polynomial is irreducible. This is something we have already shown in the chapter on rings, this was one of the exercises. And precisely this exercise, by exercise 3 of section 310, it is, I think, yes. This is irreducible over f. That means this itself is the minimal polynomial of omega over f, the field of rational numbers, which in turn means that omega is an algebraic number of degree p minus 1, and that in turn implies that the degree of the extension f omega obtained by adjoining omega to f over f is p minus 1. That means the degree of the splitting field of our polynomial is p minus 1 over f. That's what we were supposed to show. Okay, so that is the solution. Then exercise A8, but I need ink already. Exercise 8 is a generalization of this one, where in place of a prime number p, we have a general integer, positive integer n. And the claim also accordingly changes. It's not n minus 1, but it's phi of n, where phi is the Euler phi function. But this is supposed to be extremely difficult. Let's just see the exercise first. Exercise 8. So it comes with 2 asterisks, indicating that it's quite difficult. If n is greater than 1, prove that the splitting field, just like that one, prove that the splitting field of x to the power n minus 1 over the field of rational numbers is of degree phi of n. Is phi of n. For some reason the author uses capital phi, but anyway, where phi is the Euler phi function. And then there is a remark. This is a well-known theorem. This is a well-known theorem. I know of no easy solution, okay, So don't be disappointed if you don't get it, if you fail to get it. If you get an easy proof, I would like to see it. But alas, Herstein is no more. This exercise occurs in an equivalent form somewhere else, and in fact it's there that we will solve it, hopefully, because in that exercise, which comes much later, a procedure is given for solving it. This exercise occurs in an equivalent form as exercise 15 of section 5-6. Okay, so there we will see. Right now it's extremely difficult, and I am no genius. I have also not been able to think of anything. I tried to think, but it's beyond me right now. Instead, let's just move on. The next one is exercise 9. This is also somewhat difficult, it's supposed to be. If f is the field of rational numbers, yeah, this is a little annoying. Why not use the standard notation for these frequently occurring fields, so that we do not have to write things like this again and again? I don't understand this. If f is the field of rational numbers, find necessary and sufficient conditions on A and B. And sufficient conditions on A and B. So that the splitting field of, again, another polynomial. Just give me a moment, okay? So that the splitting field of this cubic polynomial x cube plus ax plus b has degree exactly 3. over f. That means, of course, a and b, because we are over the field of rational numbers, so a and b are rational numbers, and this is a polynomial over the field of rational numbers. Now we have to find some necessary and sufficient condition so that on a and b, so that this polynomial has degree, well, not the polynomial, of course, its degree is 3, but the splitting field of this polynomial has degree exactly 3 over f. And unfortunately, so far I have been unable to solve this. So this is absent here. I urge you to try the problem, and if you come up with a solution, then please let me know. I tried, I thought of some necessary sufficient condition, but things turned too messy, and ultimately I was not able to manage everything and come up with a complete solution. It's not like I have not got any idea, but I could not make all the ideas work successfully. So it's somewhere in the middle. I'm still there, I'm still stuck somewhere. I will discuss about it afterwards. If I make some progress, I will come back to it and let you know. In the meantime, I ask you, I request you to also try this, because we have been solving this type of problems for some time now. So you should be able to at least try to see what can possibly be done. Right now I don't want to say anything about that necessary sufficient conditions that I have guessed already, because they may be just simply wrong. I don't know. But you yourself try, and if you come up with anything, please let me know. So this just remains like this. And let us now see the next one. For the next one, of course, I have a solution. Exercise 10. In this one, let P be a prime number and let f be Jp, the field of integers mod p modulo p. Recall that in this text, J denotes the set of integers. So instead of writing Zp or Zp, the author is writing Jp, that's all. And now there are 3 parts, 3 subdivisions. Part A. Prove that there is an irreducible polynomial of degree 2 over n. Irreducible polynomial of degree 2 over f. That means a quadratic irreducible polynomial is always there, no matter what p is. B. Use this polynomial to construct a field with p square elements. This part B is straightforward. In the sense that we have already done this elsewhere. Use this polynomial to construct a field with p square elements. and then there is a part C which is start. Prove that any two irreducible polynomials any two irreducible polynomials of degree 2 over f lead to isomorphic fields with p-square elements. So let us once again look at the question. P is the prime number and f is the field of integers modulo p. Okay, so that's what our base field f is. Now the first thing we have to prove that there is always a quadratic irreducible polynomial over f, where again I am stressing that f is this field, because if we forget about that we may just simply erroneously think that f is the field of rational numbers, then everything will go down drain. And then we have to use this information or the polynomial, however you want to do it, to construct a field with p-square elements. And then we have to show that if two such polynomials are there, both of them are irreducible and quadratic, then using both of them we can construct such fields using whatever procedure we are going to show here when we solve part B. But then those two fields will always be isomorphic. That's what we have to show. So let us start with part A. In part A we have to show that there is a quadratic irreducible polynomial over Jp. And to do this we are not actually going to give an example of such a polynomial, but somewhat strangely we are going to calculate the number of all possible polynomials, quadratic polynomials, specifically monic quadratic polynomials, and then from that number we are going to subtract the number of such reducible polynomials. So that will give us the number of irreducible polynomials. That number will be a positive number, showing that there is at least one such polynomial. Okay, so we are going to take this approach. The number of polynomials over f of the form x square plus ax plus b is p square y. Okay, but before that, note that the number of polynomials over f of this form of course means the number of distinct polynomials. Now we are saying that such polynomials are p square in number. That is because you see the things you can change here are a and b, and each one of them can be chosen independently of the other from our field f, and f has p elements in it. So for each one of these two, a and b, we have p choices, and because the choices are independent of each other, so the total number of choices is p square. One more thing is that two such polynomials are equal if and only if the corresponding coefficients are equal. So that is why if we choose if we make distinct choices for a and b, then that will give us distinct polynomials. So that is why the total number is p square. And these are monic polynomials because here the coefficient is 1. Now among these polynomials, the reducible ones they look like this. The reducible ones are ax plus b times cx plus d, where do not confuse this a and b with this a and b. These are arbitrary constants. Okay, so in that sense they are variables also, or rather parameters. So a, b, c and d are just some elements coming from f, with this provision of course that AC is equal to 1, because unless that happens, when you multiply the terms out, you are not going to get the coefficient of x square equal to 1. For that you need this extra condition. Fine. Note that we have to consider this because it is possible once you have AC equal to 1 for this polynomial to be equal to this. That is why we cannot just simply consider here also the coefficients of x to be 1, but actually we can do that. Now we are going to show that considering these polynomials is as good as considering this type of polynomials. Next, also note that since ax plus b times, it will look a little, anyway let me use this multiplication operation. It looks a little odd writing one part here, one part there, but I don't have space. Since this is going to be equal to, keeping in mind that we have s equal to 1, is x plus b divided by a times x plus ad. It's enough to consider products like x plus alpha times x plus beta with alpha and beta coming from x. So do you see what we have done here? What we have done here is that we have taken a common out. If we do that, we will have x plus b divided by a, and then that a we have multiplied with this one. So it will be acx plus at, but ac is 1, so we are getting this. So that is why if you actually consider one such product where the coefficients of x are not necessarily 1, but then that is just again another one such product where the coefficients of x are equal to 1. So that is why it's enough to consider only this type of products, and then you do not need this AC equal to 1 extra condition also. Okay, fine. But now something else is there. and that thing is this. Now let R is T and U. R is T and U belong to F such that x plus R times x plus S equal to x plus T times x plus U. What is our aim? Because we have already seen that the total number of such quadratic monic polynomials is p square. Now we are trying to count the number of reducible ones. The reducible ones look like this, but we have seen that actually it's enough to consider just this type of product. However, how are we going to calculate their number? Is it not possible that maybe there are some field elements R, S, T and U which are not necessarily the same elements? For example, R and S may be different from T and U, but still the products are equal. If that is the case, and if we just simply count the total number of such products ordinarily, maybe we are counting more than the actual number if such things, if things get repeated in our count. So we have to first make sure that this type of things do not happen. Okay, so let's see now what we get from this. Then you multiply the terms out and then compare the like coefficients. Doing that, you will just get this. Then R plus S is going to be equal to T plus U. They are the coefficients of x, and Rs is going to be equal to Tu. They are the constant terms. Now note that I did this calculation at once. T minus S times U minus S. Let me do it like this: T minus S times U minus S. It's difficult to see why suddenly this product is being considered, but we will see. T minus S times, okay, now from this equation, in place of U minus S, we can write R minus T because they are equal. U minus S is equal to R minus T. And now we multiply, now we do the multiplication. So this gives us TR minus T square minus SR plus ST. Okay. Now if we take T common out from the first and last term, then we are getting T times R plus S minus, from here also, we need to first of all change this. Note one more thing, that in place of SR we can write TU here. So now in place of R plus S we can write T plus U. On the other hand, these two give us this. So we are getting 0. Okay. So what does this calculation tell us? So if say you are hoping for such a collapse or repetition in your count like this, as you are changing R, S, T and U. In order to keep your count distinct, you would of course not want R and S to just be T and U in some order. You would want things to be different. But now if you assume that say T is not equal to S in an order to make your two counts different. So if T is not equal to S, then what will happen? If T is not equal to S, then this factor is non-zero, but then this factor has to be equal to 0, then U is equal to S, because we are in a field after all. So in a field is an integral domain, zero divisors do not exist, so this should be equal to 0. So U is equal to S. So if you are assuming that this S is not T, but then in order to have this, S must be equal to U. So in effect, you are assuming that this factor is not this one, then this factor must be this one. But now if U is equal to S, then actually R is equal to T, but then this ends up being this one. So if that means if whatever R, S, T and U are choosing, so that these two products are equal, then you cannot make them something different. R and S must be T and U in some order. Either it's just R is T and S is U, or R is U and S is T. There is no other choice, because otherwise these two things will not be the same, and hence R is equal to T. Thus distinct products x plus alpha times x plus beta over F are distinct, or instead of writing over F, let me write in Fx. Distinct products in the polynomial ring are also distinct elements. Here the products, but we need to also say what do we mean by distinct products. Here the products x plus alpha times x plus beta and x plus gamma times x plus delta in Fx are distinct if the sets of those parameters, that is alpha, beta and gamma, delta, are distinct. If this set is different from this set. If this happens, then those two products must be different. In fact, that's what we have shown here. Okay, so now we are sure we can just simply count the number of such products and hence the number of quadratic monic reducible polynomials over F simply by looking at how many ways we can choose alpha and beta, that's just it. So the number of monic quadratic reducible polynomials over f is, okay, now actually how many ways are there for us to choose alpha, because alpha is after all coming from f and f has p elements, so there are p choices for alpha, but there are p choices for beta also, but we have to be a little careful. I mean, I thought of it in by classifying it into two cases, one where alpha and beta are distinct and one where they are actually the same, in order to avoid any potential confusion. So if alpha and beta have to be distinct and both of them are coming from f, then there are p choices for alpha, but once you have chosen one alpha, that choice is gone. Then there are p minus 1 choices for beta. That means how you choose two elements out of p elements so that the choices are distinct. That is your p times p minus 1 divided by 2 because the order does not matter. That also we have to keep in mind. X plus alpha times x plus beta is actually equal to x plus beta times x plus alpha. So when alpha and beta are distinct, this number is p times p minus 1 divided by 2. But what about that case where alpha and beta are equal? In that case, you just have to see how many choices you can make for alpha, which is just p, because the other one is also x plus alpha, that's it. And this turns out to be equal to this. So this many quadratic monic reducible polynomials we have over f, and the total number of such polynomials, not considering reducibility or irreducibility, is p square. So the number of monic quadratic irreducible polynomials over f is p square minus this number, which is going to be equal to two p square minus p square will be p square minus p divided by 2. That means p times p minus 1 divided by 2. And this number is, wait, let me just see one thing. Have I made a mistake here? P square minus p plus 2p is p square plus, no, it's okay. So this is greater than 0. So the number of our required irreducible polynomials, of course, quadratic and monic. Monic we are choosing for our own convenience to make matters simple. We just need, keep in mind, we just need to show that there is at least one irreducible quadratic polynomial. That means at least one irreducible polynomial of degree 2. Monic we have added to make things simple. And we have seen that the number of such polynomials is this. even when p has the smallest value, that is 2, still this number is 1. So in that case also there is one polynomial, and that is why this is the solution to part A. Note one thing, that this is a purely should I say existential solution, in the sense that we did not actually produce such a polynomial, but we have shown that at least one such polynomial must exist. But that's enough for the solution. Now part B. In part B, what we have to show, now we have a polynomial which is irreducible and which is a quadratic polynomial in fx. Using this, we have to construct a field of order, or a field with p square elements, and this we have already done more generally in one exercise, and that exercise is this. Let px be irreducible and of degree 2, whose existence we have just now proved by exercise 7 of section 3.9. This quotient ring of fx, quotiented by the principal ideal generated by px, is a field with p square elements. Okay, this we proved in this exercise more generally for an irreducible polynomial of degree n. In that case, a field with p to the power n elements is constructed. You can recall your results from field theory and see why this is a field, because you see your fx is after all what? A Euclidean ring, and in that Euclidean ring, it's a ring after all. It's a polynomial ring, it's a ring. Px is irreducible, so the principal ideal it will generate will be a maximal ideal in fx, and maximality of this ideal turns the quotient ring into a field. And p square elements, of course, you will be able to see why if you go back to the solution to this exercise. Okay, so this is part B. Now we come to part C. Let px and qx be two polynomials over f, both of which are irreducible and quadratic. Be irreducible of degree 2. So similarly we can create two fields, then both E1 and E2 are fields with p square elements. Okay, and they are not just simply fields, they are actually extensions of F. And this fact we have seen in the proof of theorem 531. By the proof of theorem 531, E1 and E2 are extensions of F. Okay. Now we are going to consider a polynomial over F, this particular polynomial. Now consider the polynomial x to the power p square minus x in fx. What is the something, why suddenly this polynomial? That's difficult to see right now, but we are now going to show that E1 and E2 are in fact both splitting fields of this polynomial over F. And because we know that any two splitting fields of the same polynomial are isomorphic, that way we will get the fact that E1 and E2 are isomorphic. So what do we need to for that? E1 must first of all contain all the roots of this polynomial, that is one condition, and then E1 should be the smallest extension of F in terms of degree to have all the roots of the polynomial. Then E1 will be a splitting field of this. Similarly for E2. Okay, so let's now see what the roots of this polynomial are. One of the roots we can just immediately see is 0, because if we replace x with 0, we get 0. Note that the root 0 of our polynomial, is it okay to write it like this? Or let me, okay, this will be better. Note that 0 belonging to E1 is a root of x to the power p square minus x. Fine. Now since E1 minus 0 is a field under I should write the number of elements of the, is a field with p square minus 1 elements under multiplication. It is because it's a field, so if you remove 0, the rest of the elements form a group. What the hell am I writing? Is a group group with p square minus 1 elements under multiplication. So by one of the corollaries to Lagrange's theorem from group theory, we have this: for all elements of this multiplicative group. Why? That's because this is an element, this is the order of the group, and this is the identity element of the group. And this thing can now be written a little differently like this. i.e. still a little more differently like this. For all elements in E1 minus 0. So do you see what we have finally got? Namely that this Z, which is any element from this multiplicative group of non-zero elements in E1, is actually a root of our polynomial. And additionally 0 is of course also a root. So how many roots are we getting? Here we are getting p square minus 1 roots plus 1 extra root 0. That means p square roots of the polynomial we have already obtained. But it's a polynomial of degree p square, so it is anyway going to have only p square roots. So we have found all the roots of our polynomial, and in fact all of them not only are in E1, but E1 consists of all the roots. So naturally E1 is going to be the smallest extension of F containing all the roots, because there is nothing else in E1, just the roots. It's a little strange, but still it is what it is. So E1 consists of all the roots of our polynomial, and hence is naturally a splitting field of our polynomial. Similarly, whatever we have done with E1, we can also do with E2, because there is nothing special about E1. Similarly, E2 is also a splitting field of our polynomial, and that is why they are isomorphic. If you are wondering how I guessed this polynomial, that's because I have cheated a little bit. I have seen something which we are far away from such things. Towards the end of this book, I think, if I am remembering correctly, where there are some isolated results, some maybe topics of greater interest, something like that is given at the end of the book. There I saw this polynomial, and then I realized that okay, yes, this is the thing. In fact, this technique is used to show that two finite fields having the same number of elements are isomorphic. It's in the proof of that result that I found this polynomial, and from that proof only I got this idea. So it worked here. So by theorem 534, E1 is isomorphic to E2, and that's just it. And that's where let's end the video also. And the usual things that I say at the end of all the videos, suppose that all those things I have said. So the next upload is on this coming Friday. So group theory we have done, fields we have done. So let's do calculus. Let's keep it a little simple this time. And then we will go to vector space, and all the other things will also come. So see you on Friday with calculus. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.